Welcome back to our video module on dynamics. In our previous video, we looked at a rotating translating coordinate frame relative to a fixed frame with a moving particle on it, and we identified what the velocity was of that point relative to the fixed frame. We saw that there was a component due to translation, there was a component due to the rotation of the coordinate frame, and then there was also a component due to the fact that that point was moving within the rotating coordinate frame. We named it B. Today I'd like to use this approach to understand the acceleration of a point in a rotating coordinate frame from the perspective of a fixed frame. Let's rearrange some things here. Here we go. We've just rewritten our velocity transformation on the left. We've kept our schematic of what the translation looks like between the moving coordinate frame and the fixed coordinate frame, although we seem to have lost our y-axis. And we've kept our schematic for the rotation and the relative contributions to the overall velocity. Let's take a look at an example of a relative reference frame that's undergoing acceleration, velocity, and position changes in 2 dimensions. Here's Andy Ruina at Cornell.
So I've got a spring here, and I've got some object which is not a point mass. So I want to know how this thing moves around in 2 dimensions, assuming it's got a frictionless constraint from the wall holding in place. It's not just a pendulum. It can do all kinds of crazy things.
Now let's take a look at the acceleration equation. The acceleration of point P with respect to O equals the acceleration of O prime with respect to O, plus the acceleration of point P with respect to the B reference frame, plus omega cross position of P with respect with O prime, plus omega dot cross position with P with respect to O prime, plus 2 omega cross the velocity of P with respect to the B reference frame. This is quite a mouthful. Now if we could figure out how to understand this, if we know the acceleration of that point, we can also figure out forces that are acting on that point. Let's attack this with the same approach we used to understand acceleration using polar coordinates. First, acceleration of O prime with respect to O. This is simply the difference between the accelerations of the 2 coordinate frames. So here we have the original coordinate frame. We have y prime in red, x prime in red, the original coordinate frame, y and x. And let's say in yellow, x prime and y prime has some sort of acceleration. This term takes into account the linear acceleration of the relative coordinate frame. This corresponds to earlier when we looked at the velocity change due to translation. All right, so next let's take a look at the second term. Let's scroll down, maybe to right there. The second term is the acceleration of point P with respect to the B coordinate frame. And that in that one we're going to have our x and our y, and say right on top of it we're going to have our relative coordinate frame. So there's really nothing going on, nothing different between the relative coordinate frame and the stationary coordinate frame. However, in this case we have some point P and it is accelerating, say right here. It has some sort of acceleration. The second term accounts for the acceleration of the particle. And while we're at it, the first term accounts for the acceleration of B, the acceleration of the moving coordinate frame. This corresponds to what we looked at earlier in our velocity, the relative velocity. This is like the relative acceleration. Let's take a look at our third term here, omega cross R. Third term, omega cross R. To understand this term, we're going to make our absolute coordinate frame. We're going to make our relative coordinate frame, y prime, x prime, and we're going to give the relative coordinate frame some angular velocity give ourselves some point P, and that point P is staying still. As the coordinate frame spins, we're going to see some sort of centripetal acceleration. If you're on the coordinate frame, you see nothing. All you see is that particle's just sitting there. But if you're in your stationary frame, you see omega squared r, or the centripetal acceleration. That's what this term accounts for. And if you do the directions and the cross products, you'll see that the direction of the acceleration is going towards the center. In this particular case, this is centripetal acceleration. Let's erase this right here. And the next term, let's try and understand that. The significant term here is a change in angular velocity. So this is our fourth term. Omega dot crossed position of P with respect to O prime. Let's copy the one above it. Copy that and reuse that. And this time, we're not going to give it an angular velocity. The angular velocity is going to be 0. And instead, we're going to give it an angular or a change in the angular velocity alpha. And in this case, we see that in the resting coordinate frame, we're going to see some sort of acceleration because the rotating coordinate frame is accelerating itself. We might say that this is the acceleration due to alpha or theta dot. Finally, let's look at the fifth term. This should look similar to the Coriolis term in polar coordinates, and in fact that's precisely what it is. In order to understand this term, we'll make this term number 5. We have 2 omega cross velocity of point P with respect to B. Let's go ahead and copy this from here. Erase this as it may confuse us. In this example, we're going to give the relative frame an angular velocity, and in addition, we're going to give the point some velocity. We see that these two pieces of information combine, and we're left with a term known as the Coriolis effect, or you could just say the Coriolis acceleration. We can look at the combination of all 5 of these effects, and these are all the influences on the acceleration of a particle on a rotating rigid body as seen from the stationary frame. So in summary, we have quite a mouthful, a nice big acceleration term that helps us understand the relationship between a rotating frame and the fixed frame. In our following videos, we'll explore this concept more fully. I look forward to seeing you then.